So I heard one dominant. Careful. Trick question, maybe. I had a second. Two people think it's dominant. Okay. Could be dominant. So if it's dominant, then what are the genotypes? So let's assume it's dominant. It's present in successive generations, 2 generations in a row. Top line, the second line. Why doesn't the third generation have this disease? Does it make sense that none of those 3 kids in the bottom row have the disease? Why?
Well, for the wild type.
So are their parents affected?
No.
No. So if it's dominant, if the parents aren't affected, they're not going to have kids that have the disease. Okay. So what are the genotypes of those 2 individuals, numbers 7 and 8? If plus is wild type and asterisk is mutant, what are their genotypes? Plus plus. So is there anybody on here that might be homozygous for the mutation? Is there any possibility? How do you know? Which individuals is it? 5 and 6. And that's because we know both of their parents are affected, so both of those parents, 1 and 2, have to have the mutation. It's possible that both of those parents each contribute a mutation. It's possible. We don't know. But it's feasible that we could conclude that individuals 5 and 6 are homozygous for the mutation. A little bit of practice working on pedigree analysis. Any questions about this?
You have to know what their kids' genes look like when they drive for the wild mutant, right?
Okay, so what would we have to do to individual 5 or individual 6 to find out if they're homozygous, mutant, or heterozygous? You want to do what? You want to do a test cross? Okay, so we're playing, let's assume this isn't a human pedigree. We're going to force some people to mate together and we're going to find out whether or not they're homozygous, mutant or not. Okay. This is dominant, right? So what's going to be the outcome of this cross if the genotype of individual 5, the father in this case, is homozygous for the mutation? What do all his kids look like? So let's assume they've got 4 kids. So they're all going to have the disease or not have the disease? They're all going to have it. They had to get one dominant mutation from the dad if the dad's homozygous for the mutation.
So should you see one that's not, you know who's the head?
Right. So how do you know if the father instead, let's switch colors, the other possible genotype of the dad is heterozygous? 1 mutation, 1 wild type. So if this is dominant, what would his kids look like if we had 4 kids in that case? Yeah, what fraction of the kids should get the mutation? Half, Mendel's laws. And that's why pedigree analysis requires lots of generations, so we get enough evidence altogether to make a really good decision about what's the mode of inheritance. Is it recessive? Is it dominant? And as we're going to figure out a little bit more today, is it autosomal? Is it X chromosome based inheritance? Other questions? So I've stricken incomplete penetrance from the record in terms of a goal for this course. We might discuss it along the way, but I want to let you know that you're not going to be required to know incomplete penetrance. Although, as I said last time, if there's ever any doubt about an inheritance pattern and you claim that there's incomplete penetrance, that's a pretty safe bet. Last time we met, we were talking about some big pedigrees and identifying inheritance patterns, and specifically in this case, trying to figure out what genes are responsible for conferring the trait that we're trying to map in this pedigree. And last time, review, the simple thing you do is you look for what alleles are common to every individual that has this trait. And in this case, we discovered that everybody who has the allele size 4 at A, on chromosome 1, 1A4, and individuals that have the allele size 7 at marker B, locus B on chromosome 1, all seem to have this disorder. So that suggests there's a gene in there somewhere, not necessarily either of those two loci, but there's a mutation in blue, somewhere linked to those two loci, A and B on chromosome 1, that causes this disease. And you can see that chunk of chromosome inherited from generation to generation. So we have perfect correlation between people that inherit that part of that chromosome from their mother, from their grandfather, and so forth, and prevalence of this disease. Correlation. You inherit this part of the chromosome, you get this disease. In that case, it was a perfect correlation. There's a problem with correlation, though. There are lots of correlations that you can make, like this one, right? Almost perfect correlation because between the increase in organic food sales and autism, people. What's causing autism? Must be consumption of organic food, right? They're perfectly related. As organic food sales increase, so does autism. No. That's correlation. That doesn't mean that organic food sales causes autism. It just happens to be that those data trend together, much like in our pedigree. The pattern is that that part of that chromosome is in every individual that has the disease. That suggests that something in that part of the chromosome causes the disease, but it takes more work to figure out what exactly the mutation is that causes the disease. Here's an even better example of correlation. As cheese consumption per capita goes up, so does the increase in strangulation by your sheets on your bed. I didn't even know that was a thing. But apparently, what is that? 700, 800 people a year at the right y-axis die becoming entangled in their bed sheets for a year. I don't know, I can't trust the source. Let's see, what does it say? Number of people who died of deaths, US CDC, Centers for Disease Control. So maybe a reliable source of information here. 95% correlation, 0.95. Cheese consumption and strangulation by bed sheets. Right? Correlation, not causation. So just because two things happen in the same trajectory doesn't mean that they're related. It's the only, I'll get off my soapbox now about correlation versus causation. Okay, here's the pedigree where you have to be very careful about what the pattern of inheritance is. Spend an extra 15 seconds. Turn to your neighbor and talk to them about what they think the inheritance pattern is and try to convince your neighbor that you're right. We're going to take a poll in about a half a minute. Is it dominant or is it recessive? Okay, so I'm hearing good conversations. Sounds like you're on the right track. Okay, who says that this is a dominant inheritance pattern? Okay, recessive. Okay, overwhelming support for recessive. Why does this not initially look like it's recessive? It's present in every generation. This disease, there's one person at least in every generation that has this phenotype, whatever it is, not necessarily disease. Why did most of you go with recessive in this case? Pardon? Roughly 25% are affected.
Well, is it because the two parents on one side, 11, 4, 11, 5, they have the infection, but then the offspring has the infection?
Right. So in this part of the pedigree, you notice that there, all of a sudden it skips a generation. It's in the grandparent, it's not in either of the parents, and then it shows up again. That's the typical recessive pattern. So when you look at individual branches of the pedigree, you see it skips generations. But when you look at the pedigree as a whole, it is present in every generation. So that presence in every generation in the whole pedigree does not necessarily mean it's dominant. What happened in this case? How can you have a recessive trait that's present in individual 2, 3? How did that person get this disorder? If this is recessive, so that's the hypothesis we'll go with. We're going to start with pick one, dominant or recessive. Most of you said recessive. So we're going to assume this is a recessive. Dad's genotype then has to be homozygous mutant if he's going to have a recessive trait. So how does 2, 3, their son, get this trait? Mom's a carrier. Okay, so now you can have a son that has the trait, 2 daughters, neither of which have the trait. So what are the genotypes of individuals 2, 4, and 2, 5? The 2 unaffected parents that have kids 3, 4, 3, 5, 3, 6, and 3, 7. If you have 2 parents that are unaffected, and it's a recessive trait, which one? Trick question. So what happens if they're both heterozygous? And this is a recessive trait. What frequency should we see of their kids having the disorder? Should see 25%. You can set up a Punnett square and do this. So it should be 25%. What do we observe? 50%, half of the kids, right? 3, 4, and 3, 7 both have the disease. So why is it useful to have pedigrees where you study families with lots of kids? Is 2 out of 4 statistically different from 1 out of 4? Don't make me do a chi-square test. But that's what you would do. You would ask, is 2 out of 4 statistically different from 1 out of 4? We expect a quarter of the kids will have this disorder. So I suggest you do this. Not right now necessarily. Do a chi-square test. If you only have a family with 4 kids, and you see 2 of them that have the disorder, does that rule out that this is recessive? Try it. Okay. So I think that means that we've come up with the idea that parents 2, 4, and 2, 5 are both heterozygous. That's how they can have affected kids. We have to answer a couple of questions to have those genotypes. What's the probability? We know the genotype now, 2, 4. We've inferred it based on the pattern of the phenotypes alone. What's the probability that that mother is heterozygous? This is a trick question. So it's a recessive trait.
If I don't agree with that.
If you don't agree with that, then you have to explain to me how a dominant trait skips a generation.
What if it's X-linked?
And dominant? Okay, we're skipping ahead, but I want to answer your question now because it's going to be hard for me to remember to come back to this. If it's X-linked, then the father is going to pass it to all of his daughters. And in this case, it's the opposite pattern. Father only passes it to his one son. So that rules out X-linkage. We'll see that later in class, so if you don't know X-linkage yet, that's fine. So 2-4. We already kind of answered this question. That's why it's a trick question. Hard? No? What's the probability that does this individual have to be heterozygous to make sense with the data? Yes, so what's the probability that that individual is heterozygous? 100%. Absolutely. We don't have to do a chi-square, or not chi-square test, we don't have to do a Punnett square. We've already decided that individual's genotype based on the fact that if that individual, 2-4, was not heterozygous, there would be no way to have affected offspring in the case where we assume that this is a recessive trait. So 100% probability that this individual is heterozygous. The approach to that question is different than the approach to this question. This one really is asking for that Punnett square sort of thing. If you have two heterozygous parents, what's the probability that one of their kids is heterozygous? So we have a heterozygote here, and we guessed that this parent must also be to have affected kids. So what's the probability of that individual being heterozygous? Play genetic counselor. So you set up a Punnett square. Right, the genotypes, the alleles of the two parents. And you get 50% by just making these combinations. Right, there are going to be two squares where the individual has the heterozygous genotype we're looking for. There's still a trick to this question, though. What additional piece of information do we have about this individual that can help us rule out possible genotypes? Indeed. Individual 3-5 does not have the disease, so which genotype does this individual definitely not have? Definitely not homozygous recessive. So now what's the probability that this individual is heterozygous? Right. Well, we know it's not 75% because we've already ruled out one of those four options. The individual doesn't have this disorder, so there are only 3 remaining options: heterozygous, or wild type. So 2 out of 3, or 66%, is the probability that this individual has the heterozygous genotype. This is not asking about Punnett square style. We used a Punnett square, but we've ruled out one of the 4 possible outcomes because if this individual was mutant, they would be affected by the disorder. So they're either wild type, homozygous, plus over plus. That's 1 out of the 3 options. There's a 2/3 chance that that individual is heterozygous. Ladies, on behalf of all of the men, I ask you to take pity on us. Because we have this one chromosome called the Y chromosome, which does a lot of bad stuff. The reason that our Y chromosome really sucks is because it's missing a lot of the genes that are present on the chromosome it used to be. So our Y chromosome used to be identical to your X chromosomes and our X chromosomes as well. So on the X chromosome here on left, there are a number of genes. As with all chromosomes, of course, a lot of genes. Guys Our Y chromosomes used to be X chromosomes about 100 million years ago. But in that period of time, our Y chromosomes have lost all of those genes that are still present on the X chromosome. And that's why these are called the differential regions of the X and the Y. Ladies, you've got 2 copies of all of those genes in the middle, the differential region, because you're diploid, you've got 2 X chromosomes. Take pity on us, poor guys. We're haploid for the X chromosome. Our Y chromosome doesn't have those genes that are there in the middle. So we only have 1 copy of our X chromosome genes. That is the entire sole basis for the concept of sex-linked inheritance patterns. That we, the guys, don't have an extra copy of the X chromosome. We've only got 1 copy of the X chromosome genes. So now we're going to shift from talking about inheritance patterns in general, autosomal, that is, genes that are linked to chromosomes 1, 2, 3, 4, etc., 22. Now we're going to talk about the X chromosome. So there are 2 ways that you identify autosome versus X-linked traits. One is a bias in inheritance of the trait by one sex. So here's 2 pedigrees that exhibit one disease. What's the difference? In one case, you've got a guy that has the disorder, and we're watching how he passes it on to his offspring. So this is what you should do if you ever want to know if a trait is X-linked. You do the reciprocal crosses. That term right there. So this is what it means by reciprocal. You take 2 individuals that have the disorder. In one family, you want the father to have the disease. You want to see how he passes it on to his kids. In the other cross, you want to have a mom that's affected and see how she transmits it to her kids. That's a reciprocal cross. Not that we actually cross humans, but assume this is Drosophila. Or whatever organism you want, it doesn't matter. What's the difference here? Disease 1. Where is something unexpected happening? If this is an autosomal trait, mom on the right there passes it to about half of her daughters, about half of her sons. That's what we would expect. What happens on the left side? Right, so dad seems to be, and we don't have probably enough data there for it to be statistically significant, but dad seems to pass it to all of his daughters and none of his sons. That's the part about the bias in inheritance by one sex. So when you see that sex-biased inheritance, only daughters get it or only sons get it, depending on which cross, is dad affected or is mom affected, that's when you start thinking, I wonder if this is going to be an X-linked trait. Here's another example. This is probably more obvious than the last one. What's going on here? Where are the biases? So if dad's affected, nobody gets the disease. If mom's affected, what happens? Only her sons get the disease. So now what I've done just for convenience is I've drawn the sex chromosomes on here. So males are XY, females are XX. Assume that there's a gene on dad's X chromosome that acts in a dominant fashion. Who in the next generation, feel free to draw your own pedigree, fill in whichever symbols you want, you think will accurately represent how dad passes his X chromosome to his kids. Okay, for those of you that are doing this, thank you very much. How many symbols did you fill in? How many people filled in 3? Okay, good. Right, if dad has only one X chromosome, he's going to pass it to half of his kids. Which 3 did you fill in? Which ones? Okay, so dad's Y chromosome, by definition, goes to all of his sons. That's how they become sons. So if dad passes his X chromosome on, it's guarantee you going to all of his daughters. So father passes the trait to 100% of his daughters because he's only got one X chromosome. It's got the mutation on it. So this is the inheritance pattern for X-linked dominant traits. Dads pass it to all of their daughters. What about moms? Let's assume that she is heterozygous. How will that be transmitted to her 6 kids? Still going to be 50% of the kids. Right, so you fill in 3 symbols. Is it limited to one sex or the other?
Wouldn't all the males get it?
All the males get it. Right. Or do they? Depends on the genotype of the mom. So in this case, she's heterozygous. So what's the probability that any son inherits the mutation on the X chromosome? 50-50. So you might fill in half of the sons, or in this case, 2/3, which is approximately a half. What about daughters? What's their probability of inheriting the bad X chromosome from mom? Also 50%. So you might fill in half of the daughters. So this is the difference, is how you distinguish X-dominant inheritance. From mom, looks like an autosomal trait. Half the kids inherit the mutation. It affects males and females equally. But when you look at the reciprocal cross, when dad has the disease or trait or whatever and passes on to his kids, you don't see it look like it is autosomal. Like it's 50-50, affects males and females equally. For X dominance, dad passes it to 100% of his daughters, none of his sons. Those are the critical. Hopefully at some point when you review this, you'll write out a table. These are the rules for X-dominant, X-recessive. Because if we look at X-recessive traits, there's a totally different set of patterns. This top example is why it's really important to understand why we guys can be affected by X chromosome recessive traits. Why can this father be affected by a recessive trait? Because he's only got one X chromosome. So we're hemizygous. We have half of the normal X chromosomes we normally would have. So if he's got the bad version of the X chromosome, we would write his genotype as mutant, that's the X chromosome, over the Y chromosome doesn't have the gene. So we just write a hyphen, a dash. There's nothing there. There's no gene. It's not a good gene. It's not a mutant version of the gene. There's nothing. So how does he pass that X chromosome that has the mutation onto his offspring? Just like normal. Okay, what's the genotype of the mom? Let's assume that mom is wild type. Just for this. Okay. What? Now fill in the next generation. Dad's sons get his Y chromosome, so are they affected or wild type? They don't inherit the mutation, so they're wild type. What about the daughters? They're either unaffected or they're, I heard somebody say it up here, They're carriers. How many of the daughters are carriers? All 3. And we denote carriers of sex-linked traits by dots instead of half filling in the symbols. If you half fill in a symbol at some point and it's a sex-linked trait, that's okay, I will forgive you and give you points. But this is separate annotation. Right? 100% of the daughters have to be carriers because dad passes the Y chromosome to all his sons, he has to pass his X chromosome on to all of his daughters. So if you've got an X-linked recessive trait, dads make all of their daughters carriers, none of his sons get it. What happens in the reciprocal cross? Now we've got a mom. This is recessive and she's affected. She must be homozygous for the mutation. Let's assume dad's wild type, plus over nothing. So go ahead and fill in what you think will happen in the next generation. Are there any carriers in the third gen or second generation? Who are the carriers in the second generation? The daughters. How many of the daughters? All of them. Everybody, guarantee you, because the mom's homozygous for the mutation, every daughter gets a copy, plus every son. So are the sons affected or not? So sons get one copy of a recessive mutation, but it's on the X chromosome. So they get the disease, because their Y chromosome doesn't have the wild type version of that gene. So if it's recessive and it's on the X chromosome, when dad has the trait, now it kind of looks like a normal recessive trait. It skips a generation, right? Nobody in the next generation in the upper panel has the disorder. The daughters are all carriers though, but they don't exhibit the trait. And when mom's affected, she passes it to all of her sons. So there are very clear patterns that are very distinct for X-linked dominant and X-linked recessive traits. We've just gone through a couple of examples. So it's pretty easy to distinguish the difference between X-linked dominant and X-linked recessives. The best approach, honestly, for figuring out inheritance patterns is look for whether or not the data support X-linkage first. If some piece of data in the pedigree rules out X-dominant and X-recessive, then the default assumption after that would be that it's autosomal. So autosomal is kind of like always the last resort. Rule out the weird exception cases first, because they have more strict rules about how you identify them. And whatever's left over, if it's not X-dominant, it's not X-recessive, and a couple of other types, which we're not going to have time to talk about, then when you rule out all other options, autosomal is the last choice, really. Never say something's autosomal until you've ruled out the possible X-linkage. So these are my examples of how I filled in those pedigrees. They don't have to be identical to yours.
So to be a carrier, it means that you don't display the trait, but you have a gene for it, whereas if you were to fill it in halfway, it means you display the trait and you have a gene. Is that how the pedigree works?
Sorry. So I'm glad you asked because that's always unclear, and I always forget to address this. An autosomal carrier, we half fill in the circle. Sex-linked carrier, you put a dot. In neither of those cases is this individual displaying the phenotype. So half filled in does not mean they have half of the phenotype or that they have the phenotype. They're wild type looking. That's just a symbol to indicate that half of their chromosomes carry the gene that could confer that trait in a future generation. For autosomal traits, just to be really complete, for autosomal traits, any sex can be a carrier. You just have to be heterozygous. For X-linked traits, you can't be a male and be a carrier because we've only got one X chromosome. Females, absolutely. 2 X chromosomes, you could be heterozygous, you could be a carrier. Males, there's only 1 X. Sir?
What does a line mean? Is that
Just a slash through the individual. That means they've deceased. Dead. Yeah. I'm going to see in just a second. So I just wanted to take a brief trip through a few of the pedigrees that you submitted. Thanks very much again for all of you that participated. I'm sorry I can't show everybody all of your pedigrees. But here we've got, let's see, what's the trait in the upper left? It seems to be only males are affected, right? Somebody's charting the presence of their Y chromosome through their pedigree. So maleness, it's a trait. I guess since we just discussed this, all of these symbols should be fully filled in. Yes, there is only 1 Y chromosome, so technically I'm heterozygous for a Y chromosome, but all of these males have the disorder of being male. Bottom right, some of you have really large families, which as we've discussed, in fact, a lot of you have really large families, is really useful for pedigree analysis because we get a lot of statistical certainty when we do analysis of what frequency of individuals have the trait in a generation. Is it 25%? Is it 50%? I don't know whose pedigree this was, but I thought this was a good opportunity to practice pedigree analysis again. We know nothing about, if you want to speak up, if you're in the room and you want to tell us about it, that's fine, but you can choose to remain anonymous, certainly. Dominant or recessive? Is there any part of this pedigree where the trait skips a generation? The right half of the pedigree, it skips a generation. The left half of the pedigree, it does not. So here we've got transmission from generation to generation to generation, but here it skips a generation. Right. So is it dominant or is it recessive? So if this is recessive, let's pick on recessiveness again. Let's see, and this is exactly how you normally walk through a pedigree analysis. Pick one. So let's say we're assuming it's recessive. Is there anything up here that is inconsistent with this being inherited in a recessive manner? What assumptions do we have to make if this is recessive? So half of individuals in generation 3 are affected. Does that mean that it can't be recessive, though? So assuming this is recessive, what is individual 1's genotype? What's individual 2's genotype? Homozygous recessive. So if individuals 1 and 2 have an affected offspring, what's the genotype of individual 1? Heterozygous. Or carrier. if this is recessive, what's individual 3's genotype? They're affected, it's recessive, they're homozygous for recessive. That means that individual 6's genotype has to have inherited the mutation from dad 3. So this individual also has to be a carrier. So now what do you think about that 50% affected kids in generation 3? Is it consistent with being recessive? Now it is, because everybody gets a copy of the mutation from individual 5, so everybody's got at least one asterisk. And then what's the chance of getting the mutation from individual 6? It's 50-50, right? Half of individual 6's alleles are wild type, half are mutant. So we could have some individuals that get the plus from mom, individual 6, and some that inherit her mutant chromosome. I'm not a genetic counselor. Do not take this advice. This is not necessarily a sure thing, but the data are at least consistent with this being potentially a recessive genetic trait. Okay. Any questions? Concerns, gripes, criticisms, complaints, nagging doubts? Time to engage your brains. Is this autosomal or is it X-linked recessive? If it's recessive. What's the one piece of information in this whole pedigree we're looking for? So you said it's. So if this is recessive, if it's X-linked, then individual 5, dad, has the mutation, has the trait. How does that X-linked recessive trait pass on to the next generation? Dad passes it to all the daughters and dad passes which chromosome to his sons? Y. So no sons get affected. Does that pattern match the kids from individual 5? Do all of his sons and none of his daughters, or do any of his sons have the trait? Yes. So it can't be X-linked recessive.
But couldn't they just get it from the mom? The son?
So if mom's a carrier, then the sons have a 50-50 chance. But what about the daughters?
They could just be carriers.
They could be carriers. So do we have enough information to decide whether or not this is X-linked or not? So then we'd have to, I apologize to if you're in the room, we'd have to set up some additional crosses between family members to try to figure out whether or not this really was X-linked or autosomal. We're not going to go there. We've already gone too far there. So yet more practice of, and this is again, like I said last time, this is when it's really important for you to own up to the reality that sometimes there is not one clean answer in a real pedigree. But as a geneticist, you get faced with this often. You have to know when there is no answer, and you have to be able to readily admit, I don't have enough data. There is no answer. And I know that's uncomfortable in the classroom, but it's also reality. You already knew I was a mutant. Who sees numbers here? Does anybody, okay, thank you. Does anybody not see a number in either panel? I'm diagnosing people with color-blindness right now. Anybody? I don't see numbers in either side. Which, for those of you that see a number, is it on the left side or the right side? But you don't see a number on the right side. Okay. Okay? So here's what's going on here. No, those of you that only see a number on one side, you're fine. This is a pair of pictures that are normal vision, and the right side is a copy of the left side that I've made colorblind. So those of you that have normal color vision, what I see, these two pictures are identical in color. So you're seeing on the right the way I see the picture on the left. So I don't see any number on the left side or the right side. So that's kind of like what it's kind of like to be colorblind. Right? That's a mutation in color vision genes that are in that differential region of the X chromosome. So there's a gene called red opsin that controls the absorbance of red light in the retina. So it allows you to detect red light. But some of us have mutations in that gene, and we don't have opsins on the Y chromosome, so which sex has colorblindness more frequently? Men. Because, ladies, most of you have 2 copies of the X chromosome. All of you should. I'm not should. Oh man, I'm gonna get in trouble. I better shut up. It's almost time to go. Good. Most women have 2 copies of the X chromosome, have 2 copies of the red opsin gene. So if you inherit 1 copy of the mutation, you still have probably normal color vision. But guys, if we inherit that mutant version, because it's X-linked, this is why colorblindness and other mutations are passed from maternal grandparents to their grandsons. So my grandfather on my mom's side has colorblindness. My mom's a carrier, and I happened to get the bad version of her X chromosome. So she's heterozygous. So I had a 50-50 chance of getting the good chromosome or the bad chromosome. I got the bad version, so I'm colorblind. What about my sisters? So this is me. What are the genotypes of my sisters? What's the probability that they're carriers? Mom has 2 X chromosomes. She passes 1 of them to each daughter. So the probability of being a carrier is 50%. Right? There's a 50-50 chance that any daughter inherits the mutation. So maybe half of my sisters, maybe Patty's a carrier and Jennifer isn't. We'll never know until they have kids. Then we'll find out if this mutation gets passed on to future males in my lineage. Let's see. I've got 2 daughters. What are their genotypes? Am I breaking some sort of law or something? What are the genotypes of my daughters? Don't tell anybody. If I've got a mutant X chromosome, then they both have to be carriers. So I shouldn't have had kids. I'm perpetuating this genetic mutation. It's going to get passed on to their potential sons, although my oldest daughter said she doesn't want to have kids, but she wants to have a lot of nieces and nephews. So she's trying to convince our 4-year-old that she wants to have kids. I don't know. I'm not getting into it. I stay out of that conversation. So what we didn't get to today, which is fine, was following up on that hereditary deafness pedigree. A lot of you, we might cover it a little bit in class next time. A lot of you got the right answer, those of you that submitted it. I do want to show you that you did arrive at the right answer, but we just don't have time to do it today. So we've got office hours right now for a little less than an hour. I have to leave early. Come visit me if you'd like. And this afternoon, I'm emailing back your exams and posting the key.